So if you clicked on this video, you probably already know about the Netflix show Squid Games. We're going to be talking about one of the games in particular, which is more interesting from a probabilistic standpoint. So in one of the games, they have a series of players who are going to be traveling through 18 bridges, and at each point, at each of the 18 points, they have two options to go either left or right. Now, the interesting thing about this is that one of their decision options is going to get them killed. The glass will break and they'll fall to their death. So only one of them is actually going to be able to support their weight. So the question we're asking is, what is the probability distribution of an individual player surviving the game, basically? So players are numbered 1 through, in our case, 16. In the show, there are 16 players, but we're going to be generalizing this, of course. We'll say that there are n equals 18 bridges, for instance, n bridges, and there are some number of players. More specifically, we'll be wondering about the chance of survival of some individual player which is at position I. So for instance, if I equals 3, we're talking about what is the probability of player number 3 surviving. So the way we're going to formulate this to begin with is we're going to construct a probability distribution. We're going to say the probability of player I surviving given there are n bridges, and we're going to need to figure out an expression for this. Now, the key insight here is that if you have your first option here, so let's say player number 1 is at this bridge decision, he can either go left or right. Whatever his decision, it doesn't tell us anything at all about the n-1 bridges in the future. Because of this, you can kind of consider this to be you can kind of consider the n-1 bridges in the future to be an entirely separate game on one fewer bridges. So the key thing here is that player 1 is the only source of the randomness. Player 1 decides everything, left or right. So 50% of the time, player 1 is going to get the right answer. So we're going to have 50% of the time something happens, and then the other 50% of the time something else happens. And for each case, we need to know the probability of player I surviving, the player I that we're interested in. So I'll go ahead and draw some more people, and let's say that this is player I right here. So in this case, he's 3, just in the example image. So in the one half of cases where 1 makes the correct decision, we're going to have the probability, and we know there's going to be n-1 bridges if player 1 gets the correct answer. And if player 1 gets the correct answer, player 1 survives, which means we're still going to be player I. The original player I we were looking at is still player I if player 1 makes the correct choice and survives. If player 1 makes the incorrect decision, then he's going to be eliminated, which means that our player, the one that we're interested in, is now player I-1. For instance, once 1 is eliminated, the players are basically renumbered. So we were looking at 3 before, and now we're looking at 2. And there are still n-1 bridges because if player 1 gets the incorrect decision, we know that the other one is the correct answer. So there's no more probability to consider for that bridge itself. And this is basically the entire recurrence relation that you'll need to solve the problem. The only thing is that we're basing a large problem in terms of smaller problems. We can't keep making the problem smaller and smaller and smaller forever. Like we can't just keep subtracting 1 from these values, so you need to have some kind of boundaries that you'll need to check. So we'll impose the conditions that I should be greater than or equal to 1. We're talking about like player 1, 2, 3, etc. It should never hit 0. And the number of bridges, we'll say, should always be greater than or equal to 0. If there are 0 bridges, of course, the game is over. So we need to make some base cases for these boundary conditions. So if we're looking at player 1 and there are n bridges, that means that player 1 is the one that we're interested in. There are n bridges remaining, and player 1, the one that we want to know the survival rate of, has to make all of the decisions. That basically means getting heads on n coin flips. getting in heads on in coin flips. Every single one you have to get correct. And so it's basically just going to be 1/2 times a half times a half times a half n times. So that's 1/2 to the n. And the only other base case we need is the probability that player I survives given that there are 0 bridges remaining. 0 bridges remaining means the game is over, so that just means there's a probability of 1. So given this recurrence relation right here and these two base cases, we basically already have the probability distribution that we're interested in. Just to demonstrate this probability distribution, I've implemented this in Python, something to calculate this probability distribution efficiently, and we can just input n equals 18 on the command line here, and this should simulate the probability distribution that is present in the actual Netflix show, where there are 18 bridges. And we see that, for instance, the main character, I believe, was player number 16, so there was actually a 99.93% chance of him surviving. And you can see the probability distribution for all of the other players that could have survived. And you can of course throw different values in here. For instance, we can go all the way up to 40 or whatever you want. It'll because we're using the fractions library, these numbers will be exact. There's no precision loss for these calculations, so they're perfect. Oh, also, I'll put in the description a link to a GitHub repository which has this file and one other one that we're going to be talking about later. So back over here, we did the previous probability distribution in terms of a recurrence relation, which makes the problem easy to think about but is perhaps inefficient. You need to memorize a lot of repeated calculations, basically, in order to make the algorithm for calculating it efficiently. There is another alternative way that we could have solved this. We could have made the observation that if we're interested in player I surviving, that means that there are I-1 players ahead of us. So what needs to happen is we need the number of failures. So we'll look at it this way. So each bridge, we can actually, instead of making the decisions, we can just look at them as basically coin flips. Suppose like on bridge 1 we get the correct answer, someone gets the correct answer. Bridge 2, someone gets the correct answer, next one incorrect, incorrect, correct, incorrect. So basically, for player I to survive, the number of incorrect answers has to be less than or equal to I-1. As soon as there are at least I incorrect answers, that means that player I will get eliminated, because one player is eliminated every time there's an incorrect answer and we're player number I. Now, equivalently, because there are only two options, that means that we need the number of correct answers to be greater than or equal to the complement n minus I-1. So how can we formulate this? We know that the probability of getting the number of correct answers equal to k, some integer k, is going to be all of the different ways that you can distribute k check marks in observations. So basically there are n items that can be check marks or x's, and we want to select k of them to be check marks. This is a convenient notation, just n choose k is how you say this. And this expression right here is just going to be the number of ways to distribute k check marks in observations. And so this is just a number. This is going to be like, for instance, like 40,000 or something like that. To get it to be an actual probability, we need to divide by the total number of basically possible observations. So these are binary, basically. These are just like for instance, this is 1, 1, 0, 0, 1, 0. These are just binary strings. And so there are 2 to the n, or you can think of them as coin flips. There are n observations, so there are 2 to the n possible sequences, so we just need to divide by 2 to the n. So 1/2 to the n times n choose k. And for those who are interested, n choose k is actually equal to n factorial over k factorial n minus k factorial. So this is how, if you were going to implement it in terms of some programming language, this is how you could choose to do that, although there are more efficient ways to do this, given that we're going to be taking a sum, but we won't get into that. So what we need to say is that the probability that player I survives, given there are n bridges, is equal to, so we want there to be, as we determined up here, at least n minus I minus 1 check marks. So we need to do a sum where k ranges from n minus I minus 1 all the way up to n, and we need to add up all the probabilities of getting k check marks for each of those, which we already know is 1 over 2 to the n choose k. So basically this is saying k is the number of check marks. We want to include n minus I minus 1 all the way up to n. So basically getting, if we need 3 correct answers, it's 3 correct answers is okay, but also 4 correct answers, 5 correct answers, all the way up to the upper bound n. And one thing that we see right here is that this 1 over 2 to the n does not have k in it. So we can actually factor out of the sum over here. So we can just say that the probability that player I survives, given that there are n bridges, is just going to be equal to the sum of k equals n minus I minus 1 to n of n choose k, and then we just normalize that by dividing by 2 to the n. Now, just for those who are interested, we'll now take a look at a slightly more complicated problem. So we'll have the same setup where we have these players that are going to be making these decisions, and for instance we'll have like player 1, 2, 3, and 4, and we'll be looking at some player I. But the difference here is that we're still going to have n decision points, but at each decision point, instead of having 2 possibilities, we're actually going to generalize it and say that we have k-naught probability, k-naught options for each one. I'll explain why we're using k-naught instead of k in just a moment. So at each decision point, a player will walk up and choose one of the options. For instance, if they get it wrong, then there are just these k-1 options over here that the player can choose. If they get it right, they just move on to the next area over here with another k-naught possibilities. So we can formulate this really easily using the same kind of recurrence relation breakdown that we talked about in the first problem. So we can say that the probability that player I survives, given there are n bridges, but we need a little bit more information now. We need the number of bridges in this first area here that we're looking at. So that'll be k. Initially, k is equal to k-naught, but as we make a decision, for instance, the first person that gets something wrong, now we're using k-naught minus 1. And if someone gets another wrong answer on the same decision point, then it'll be k-naught minus 2. So we just need to keep track of that number as we go down. So this is basically looking at player I, given there are n decision points, which is groups of bridges, basically, and at the current decision point, there are k options, or k bridges remaining. So we can break that down like this. Player 1 is still going to be the entire source of all the randomness, so they will decide a bridge to go down. There is a 1 in k probability that they get the correct answer. So in that case, because they got the correct answer, they're not eliminated, which means we're still talking about player I. But because they got the correct answer, there's now fewer bridges. So there's now n minus 1 bridges. We move on to the next group of bridges down the line. And instead of k, we actually go back to having k-naught bridges here. You see, we have k-naught bridges because we're going to a new decision point. So that's the probability that player 1 gets the correct answer. So the alternative probability, the complement of it, 1 over 1 minus 1 over k, is the probability that player 1 gets the incorrect answer. So we need to talk about that probability. So player 1 got the incorrect answer in this case, which means that player 1 is eliminated, so we move up in the ranking to player I minus 1. Because they got the incorrect answer, we're still on the same bridge, so there are still n bridges. Now the important thing here is that we made a decision and we, for instance, eliminated one of these bridge options that we had, which means there are only going to be k minus 1 bridges, k minus 1 options at the current bridge that we're still working on. And so this is the entire recurrence relation that we need. We just need to handle the base cases. So again, we'll just enforce that I is greater than or equal to 1, since we're talking about the number of the player in the sequence. N is again going to be greater than or equal to 0. And so the new requirement is that k should be greater than or equal to 1. And also k naught should also be greater than or equal to 1. But this is really just a constant for the game. We don't have to consider it in the recurrence relation because it's not a variable. It's just a constant. So we need these base cases for the decision logic. So we know immediately that if we are looking at player I, there are 0 bridges and there are k options at the current bridge. In this case, the k options at the current bridge is really meaningless because there are 0 bridges. But in any case, because there's 0 bridges, the game is over, so the probability of survival is just 1. Now for the next base case, the probability that player I survives given there are n bridges and only 1 option at the current decision point, that's going to simply refer to a smaller problem of player I surviving given there are n minus 1 bridges and k naught decision points. So basically, because there was only 1 option, that's like this case up here, where we've removed everything but this option, so it has to be correct. So player 1 doesn't have any choice. They'll decide that one, it is correct, and we move on to the next k-naught bridges at the next decision point. Now the only other base case we need is the probability of player 1 surviving, given there are n bridges and k options on the current bridge. So what this is going to be is basically, by our assumption, n is greater than or equal to 1. So we don't have to, it's not possible for n to be 0. So n is basically the number of bridges that we're looking at, where the current bridge has k options. So on the current bridge, we have a 1 in k chance of getting the correct answer. And then on all of the n minus 1 bridges in the future, there's going to be k naught options for each one of those. And because we're player 1, and we're talking about player 1 survival, we have to get the correct answer every single time. So this is going to be 1 over k naught to the n minus 1. So basically, we have to get the correct answer on the current bridge, which is 1 in k, and then the correct answer on all future bridges, which is more difficult, 1 over k naught to the n minus 1. It's more difficult because k naught might be 4 and k might be 2, something like that. But this is how you break down the probability. So with this first recurrence relation that we talked about here, and then also these 3 base cases for the recursion, we can fully compute the probability that player I survives given there are n bridges. And in this scenario, if you just wanted to start the recurrence relation, you would say the probability of player I surviving given there are n bridges is going to be equal to the probability of player I surviving given there are n bridges and k naught decision points, the first one. This is only important if you're going to be doing it in a programming language, because you'll probably want the input to be something like this, but it's going to be implemented with this third parameter k, which is only used internally, really. So now we can go back over here and we can take a look at this more general program, which I'll also include in the GitHub repository. See the description if you want a link to that. But if we run the general program, it'll tell us that it wants the number of bridge groups, so for instance 18, and then the number of bridges per group. So if we put 2 for this, that'll be 18 bridges and 2 options per bridge. This should be, if you take a look at the previous program, exactly identical to the probability distribution for the basic program that we were looking at before. Of course, the difference with this is that it's more general. We can say that there are 3 options per bridge, in which case we get this entirely different probability distribution. Before, player 16 had a 99.93% chance of survival, but now player 16 only has a 23.64% chance of survival. So the game is much harder now by having 3 options instead of 2, which is exactly what we would have expected. So this will just give you the perfect probability distribution for each of the cases, and that's it.